I've spoken previously about electromagnetic waves and that electromagnetic waves propagate perpendicular to both the electric field and the magnetic field. In a vacuum, an electromagnetic wave travels at approximately 3.0 times 10 to the 8 meters per second. That is super, super, super fast. That's about 300 million meters per second, which would go around the Earth about 7.5 times in 1 second. But that's in a vacuum. Now, if we're talking about different materials, then we're talking about the speed of an electromagnetic wave like light traveling at different velocities. And so I want to talk about the properties of both reflection and refraction and show you how important the velocity at which light travels through different media manifests in the degree to which light bends at the interface between two different media. So to begin, let's start with a light ray that is traveling through some medium and it's reflected. So we're talking about reflection right now. And so when you're talking about reflection, you see these dotted lines that I've drawn. So you can imagine the horizontal solid black lines are the interface between, say, two different materials, like, for instance, air and water. At the surface of the ocean, for instance, you can imagine an interface of the air and the ocean water. Okay, so that's horizontal line is the interface, and then the dotted line is perpendicular. And you'll see in a second why this is important because it allows us to find angles. Now, with reflection, we're going to say that the angle between the incoming ray of light, that is going to be the angle of incidence. So I'll call theta I, and then it hits the interface and it bounces back. And it turns out that with reflection, so I'm going to go theta R, it turns out that the angle of incidence is equal to the angle of reflection. So that's pretty easy. But here's where things change because when light hits an interface, some of it reflects just like you saw, but then some of it is going to actually refract, i.e., it's going to go across the boundary. And when it goes across the boundary, it might bend. So I want to talk about why it might bend. It comes down to this idea that for different materials, you have different what are called indices of refraction. And so an index of refraction, n, is equal to whatever the speed of light is in a vacuum. And that's often given the symbol c. If you see c, that means the speed of light in a vacuum divided by v, and that's the velocity of the light in some material that is not a vacuum. Just for reference here, we're going to say c is equal to approximately 3.0. It's really like 2.998, but let's say 3.0 times 10 to the 8 meters per second. That's super fast. 7.5 times that would go around the Earth in 1 second. Okay, so that's the fastest that light can travel. So if it goes in any other medium, it's going to slow down. So look at this ratio, c divided by v. So if the maximum v can be a c, then the maximum, like, for a speed of an electromagnetic wave in a vacuum, if it's going no faster than c, then the index of refraction in that vacuum would be c divided by c, which is equal to 1. Now, if any other material is in play here, the speed of light is going to be less than 3.0 times 10 to the 8 meters per second. And that's because different materials have different atoms and molecules. And so electromagnetic waves like light have energy associated with them. And so if you can imagine when that energy encounters different materials, the atoms and molecules in that material can momentarily absorb that energy and then re-emit it. And so while it allows the electromagnetic wave to continue to propagate in that medium, it slows down that propagation because of that emission and re-emission of energy. So it turns out that in any other medium, the speed of light is going to be less than c. So if you have c divided by something that's less than c, n is going to be greater than 1. So the smallest possible value that n can be is 1, and it can certainly be greater than 1 if you have some velocity v that is less than c in another medium. So let's go back here on the left and let's say that we've got some material 1, and so it has index of refraction 1, and some material 2, which has index of refraction 2. And so we can think of the angle of incidence as the same for reflection as for refraction, but now it's not so simple where we know that the second angle is exactly the same. Now we've got some angle, and I'm going to give that a capital R for refraction. And so the refraction angle, that is the angle between the perpendicular and the light ray, might not be the same as the angle of incidence. And so we can determine what that refraction angle is going to be by something that's called often Snell's law. And what Snell's law states is that n1 sine theta 1 is equal to n2 sine theta 2. And it turns out that when theta is very small, which it often is, you can approximate this as n1 theta 1 equals n2 theta 2. And that makes it even easier to think about this. Because quite simply, if you have different ends on each side of the boundary, you're going to have different thetas on each side of the boundary. And so looking over on the left, it looks like we have the light ray starting to go more towards the perpendicular when it goes into medium number 2. And so what you have on the left is you have your refraction angle is going to be less than your angle of incidence. And so if you look at the relationship, so the refraction angle is essentially theta 1 in Snell's law. And so if it's less than the angle of incidence, which is going to be angle 2, then what does that tell you about the ends? Because you have to preserve the equation, right? So if theta 1 is less than theta 2, then n1 must be greater than n2. And so what that means is that the index of refraction on the other side, n2, is bigger than n1. And look again at the index refraction equation. If the number gets bigger, it means that things are going slower. So a general rule of thumb is that if you go between two different materials, if the light ray slows down, then the light ray is going to go closer to the perpendicular. Now let's go over to the right and do this again. And let's say now that we've got index of refraction 1 and index of refraction 2. But over here, we had n2 greater than n1. And that is why we had the refraction angle getting closer to the perpendicular. And so now let's say that n2, I'll stick with my color scheme here. Let's say that n2 on the right is less than n1. Okay. And so what that means is that the light ray is going faster in n1, i.e. up top, than it is in n2 on the bottom. So if I have, say, the same incident angle, so now I'm just going to go ahead and call the incident angle theta 1. Now what's going to happen is, since n2 is less than n1, it means that it's now going faster when it gets over to n2 compared to n1. And so now what's going to happen is it's going to go something more like this, away from the perpendicular. Let's call that theta 2. And so when you have an interface, and once the light beam crosses the interface, it goes faster, it actually moves away from the perpendicular. And again, this is because of Snell's law. Now, this time, theta 2, which is on the bottom, that goes up. And so that means that the N1, which is over here, must go down to preserve this equation. So to review, when light rays are incident on the interface between two different materials, say air and water, when the light ray reflects, it's going to reflect at the same angle that it was incident. But some of the light refracts. It transitions from one material to the next. When it transitions from one material to the next, it may interact more or less with the atoms and molecules of that material, meaning the propagation of the light might be faster or slower in that given material. And so we use the index of refraction n as a gauge of the velocity of light in a particular medium. The lowest possible value n can be is 1. That's when the light is traveling in a vacuum, i.e. c, and so n is c over c. But in any other medium, it slows down, and so it's less than c, and so it's c divided by a number less than c, so it's greater than 1. So the bigger and bigger and bigger and bigger the n gets, the slower and slower and slower that light is moving. And so if you look at both the upper left and the upper right, if you have a situation where the light goes from something that it travels faster into something that it travels slower, you can think of it as kind of getting pulled in by the perpendicular. The refraction angle is smaller relative to the incident angle. Now on the right, if you go from a medium where the light is going slower to now going faster as it goes past the boundary, now you can think of it as kind of escaping, getting away from the perpendicular. And so in that particular case, the refraction angle, theta 2, is going to be greater than the incident angle, theta 1.